this supermassive black hole is the capture of a small compact object like a small black hole of stellar mass by one of this giant black hole. Now, I have an animation in a second. It's a bit noisy. The gravitational wave is converted into a noise. The frequency is accelerated by 1,000,000. Otherwise, your ear would not see anything. But it shows you, it's a cartoon on how this source will behave. So we will detect a gravitational wave from almost 100,000 orbit of the small body around the big body. And then you will hear what happens. Can you hear the sound? I hope you can hear the sound. So I don't know if you have seen it. It's a very complex orbit. It's non-Keplerian because you're general relativity at full speed. But everything ends abruptly when the body crosses the event horizon of a black hole. If there is no event horizon, that's not the right scenario. So you realize what kind of test of general relativity this is. And it's curious that the people are thinking to various mechanisms with which this extreme mass binary can be formed. Recently, people came with the idea that this could be a passing by star that captured by going through the accretion disk of the black hole loses energy and inspiral in the disk. And very recently, XMM Newton has detected a blip. You see here in this cartoon in the bottom here. This is radiation from a supernova. It's very likely one of the small bodies going through the disk of the central black hole of the galaxy. The other, I mean, well, I think this I'll skip in the interest of time. So the other extreme of this plot you access is the regime where these two bodies are very much separated. Now, when these bodies are very much separated, it means that they are so far away from the final merger that this is basically a non-transient source. So it's a steady source in the sky, periodic. And so this will be our only chance to do non-transient gravitational wave astronomy. We are talking here various kinds of sources. So one is compact binaries in our galaxies. These sources are not very strong. So it must be nearby our galaxy and the local group. But even the black hole binary that LIGO is detecting, they have been in the LISA band for some time. I'll give you a little bit more detail in a second. So let's look at this galactic astronomy, galactic gravitational wave astronomy. We expect that LISA will be able to discriminate tens of thousands of binary formed mostly by white dwarfs in the galaxies. Thanks to the long integration time, LISA is taking data for many years, so the frequency resolution is much less than microhertz. So one should be able to distinguish this. These are monochromatic signals, right? They are all, you know, it's a gravitational wave at one frequency around millihertz. And so one should be able to discriminate and count all the sources and measure some parameter of the sources. And so, for instance, on the right, this colored thing you see here is a simulation of the census of binary in the galaxy that LISA should be able to do. And the blue dots, I think, is the white dwarf counting of Gaia. So, I mean, the crossing this kind of census with the standard electromagnetic census will be an extremely powerful investigation of the galaxies. These are so abundant that all in all, the one that you cannot discriminate one from the other will form a foreground. This is, in a sense, a limitation for the instrument, but also is a very interesting foreground to be studied. And I stole a few view graphs from a recent talk on what you can do with this information. You may see it's, I can barely read what is written there. You remember, I'm a plumber and instrumentalist, but I mean, the people seems to be able to do many things about it, to learn many things about the galaxy by doing gravitational wave astronomy of the galaxy. Even more impressive, or at least impresses me, the people have calculated recently that exoplanet around those binary system would definitely give a distortion in the signal, which is detectable with a detector like LISA. The black hole of LIGO, you know, these black holes are two binary made by two black holes of a few tens or hundred of solar masses. They spin together, and they start spinning together when they are so separated that their frequency of revolution is exactly in the LISA band. They will spend a year in the LISA band, then speed up, speed up, speed up, and then a few hours before the event, or a few days, depending on the mass, before the detection by LIGO or Virgo, they will disappear from the LISA band and enter in the band of the ground-based detector. And the people calculate that having the signal from LISA and the ground-based detector greatly improves the precision with which you measure the parameter of the source. And so any deviation from general relativity is measured with much higher precision than with a single detector, whichever the detector. So here, if you take one of this cartoon, this graph here are single detector measurement of some parameter. And you may see this is 10 to the minus 2. And when you do joint observation, you go down by almost a factor 10. So this will be a very high accuracy general relativity laboratory. The data analysis is a nightmare, though, because LISA, you have seen that this is so full of signals that it's totally different from ground-based detectors that are noise dominated. This will be signal dominated, and the community is making big effort to simulate the situation and convince and be convinced that you can discriminate the signal and extract the abundant science. And if you want to join this, LISA data challenges are becoming more and more complex with more sources in the data. One group generates simulated data, and other groups, without knowing, do a blind search and try to show that we are able indeed to extract all sorts of signals from the data series. Okay. Now I have to talk about LISA Pathfinder, right? But to talk about LISA Pathfinder, I have to do a big shift of gear and talk about LISA as an instrument. I don't know how much you know, but LISA is 3 satellites and that go around the sun, and each satellite sends and receives 2 laser beams from the other 2. It's through a telescope. You need a telescope. The distance here, the size of the mission is 1 million kilometers, 2.5 million kilometers. And the 3 satellites are put in orbit around the sun on 3 heliocentric orbits, very similar to that of the Earth. And for a magic of celestial mechanics, you can pick this orbit such that the 3 satellites form a triangle that goes around the sun forever without the need of any maneuver or using rockets and so on. And it's very stable. The relative velocity of this satellite are in the order of meters per second, while the absolute velocity are many tens of kilometers per second. And the basic measurement element, and now I'll try to convince you of something, is this one. One satellite that I call the emitter sends a laser beam to a second satellite. And when the laser beam is received here, the frequency of the beam is measured. It's measured with an interferometer, but it's a measurement of the frequency of the beam. Now, the prediction of general relativity is that if the beam propagates through a curved space-time due to the gravitational wave, it gets a frequency shift. So the color, this is greatly exaggerated, this cartoon, but the color changes and the relative frequency shift is proportional to the metric perturbation. So to the gravitational, to what the people consider the gravitational wave signal. Right? Even more important, this frequency shift changes in time, oscillates with the frequency of the gravitational wave. So for LISA, millihertz, right? And in 20 minutes, this goes up and down and the color changes. And indeed, it is the time derivative of the frequency shift, which is proportional to the Riemann tensor that I personally consider the real true physical signal. So if you want to measure curvature, you have to measure the change in frequency of this beam? Easy, right? You have an interferometer, you measure the frequency, you see it going up and down, and that's your gravitational wave, right? Unfortunately, as you may know, there are much more mundane way of shifting the frequency of a beam. For instance, if you move either the source or the receiver, you change by Doppler effect, you change the frequency. And if the velocity is changing in time, like in this cartoon, then it's not surprising that your time derivative of the frequency of the received beam is, yes, proportional to the curvature of gravitational wave, but it's also proportional to the difference of the acceleration of the source and the receiver, both relative to the local inertial frame. So how you distinguish, right? And unfortunately, very soon in this game of studying LISA, we noticed that because when you put a satellite in orbit and 1 astronomical unit from the sun, the satellite is hit by the solar radiation, and the solar radiation, which exerts a force by radiation pressure, and the solar radiation is not constant, it's fluctuating in time. And so this would accelerate in a noisy way the spacecraft by an amount which would cover any interesting gravitational wave signal. And so what you do? Well, the trick that was invented very early in this game was, okay, let's carry an inertial reference with a satellite. How you do that? Well, you take a test mass, a piece of material, and you put inside the spacecraft without touching it, no mechanical contact. Now the test mass is shielded from the sun, so you don't have the problem that is pushed by the sun and so accelerate. And so you can, provided you can do this non-contacting, you can use the test mass as an inertial reference. Before I go a little bit more in detail, this non-contacting thing is a tricky thing, right? This is a cartoon where the satellite shakes because it's hit by the solar radiation pressure, and the test mass stands still because it's not disturbed. In reality, the solar radiation pressure will push the spacecraft, and very quickly the spacecraft will hit the test mass. And to avoid that, we have to play an active trick. We measure where the test mass is inside the spacecraft, or where the spacecraft is relative to the test mass, and we feed this information to a set of thrusters, right? Rocket, the little rocket that pushes the spacecraft, to keep the spacecraft centered on the test mass. This way, the test mass can go untouched by anything, so very inertial, and the spacecraft actively try to stay centered on the test mass without colliding with it. But now you have a measure of the acceleration of the displacement of the spacecraft relative to the test mass. You say, this is the inertial frame, so I can measure the acceleration of the spacecraft and correct my data for the acceleration and recover the gravitational wave. In reality, it's not that perfect, because even the test mass will have some stray acceleration. There is a lot of things that can disturb a test mass, even if you don't touch it when it is inside the spacecraft. And so it's not surprising that in my formula before, this time change of the frequency of the laser beam is the gravitational wave. There is no acceleration of the spacecraft anymore because I have corrected the data for it, but I'm left with any acceleration that the two test masses will have relative to the local inertial frame. And this is, in a sense, is the subject of the rest of the talk, this acceleration of the test mass and how you try to make those test masses not accelerating relative to the inertial frame. This is not the only entry in the error budget. You have to measure the frequency of the beam. Remember, you have to measure the frequency of the laser beam you receive on a satellite. You do that with an interferometer. Interferometers are noisy, so you're adding noise here. But it turns, this is a plot of the sensitivity of LISA. I don't pay too much attention to this, but look at the frequency range. And it turns that the stray acceleration of the test masses are limiting the sensitivity of LISA at frequency below, say, 10 millihertz or a few millihertz, while the interferometer, the error you do by measuring the frequency only sets in above some 10 millihertz. And now remember, LISA is a low frequency detector. It's not surprising that if you look at all the sources we expect to see with LISA, most of the signal to noise ratio is accumulated at low frequency, where you are dominated by the acceleration of the test mass. So the problem of making a sensitive space-based gravitational wave observatory is to keep the acceleration of these test masses low. Now we're physicists, right? Let's put number. What does it mean making those acceleration low? So this is a plot of the acceleration noise you can afford and have LISA as we plan to do it. So this is a noise plot. That means you have to be, the acceleration of your test masses must be below this black line, right? It's noise. So the smaller, the better. Now, this is a spectral density that may be complicated, but look at the frequency scale. This is half a day, right? And look at this scale. This is meter per second square. So the acceleration of gravity in the lab or in your room is 10 in this scale. So what you're trying to do is to suppress acceleration on those test masses such they do not exceed femto-g, 10 to the minus 15 times the acceleration of an apple on the surface of the Earth. That is very hard to test on ground. Nobody came with an idea on how you measure 10 to the minus 15 if your environment has an acceleration of 10 meters per second square. And even if you try to do this in space, there are other missions that requires inertial reference test masses. These are the gravitational GOES and GRACE are gravitational mapping missions. You see that they all require test mass free of acceleration, but their requirement that this is a logarithmic scale. So for instance, GRACE requires something 1,000,000 times less demanding than LISA. And by the way, when LISA came to the ESA system, the only mission that was in view was GRACE. The other one were not even a project, right? So you have a problem. You have to show that this is achievable. And you cannot do this on ground. So in the early days, when probably most of you weren't born, ESA said gravitational wave is the future of astronomy. We want to be in gravitational wave, but we cannot afford to put 2 billion on a mission that could not even work, right? So we have to find a way of demonstrating that you can put 2 test masses in such a good free fall that we can build LISA. Fortunately, most of the disturbances on the test mass that accelerate the test mass, electrical field, collision with molecules, any sort of disturbance is local, right? So to make a significant test, you don't need these 2 test masses to be separated by 1,000,000 kilometers like in LISA. So the idea of LISA Pathfinder is, okay, take everything you were using, take everything you were using to measure the acceleration, to measure the frequency of this test mass relative to the one at 2,000,000 kilometers, and put the second test mass in the same satellite, like here, right? And measure the relative acceleration of the test masses. If you are good at making these test masses free of any parasitic force, you should see no acceleration between the 2 test masses. And so you may say, this is one of the LISA arms, shrink from 2.5 million kilometers to 40 centimeters approximately. So that's what we built, 2 test masses in a single satellite. There are 2 interferometers here. One interferometer measures the relative displacement of those 2 test masses, and so measure the relative acceleration. The other interferometer measures the position of the spacecraft relative to one of the 2 test masses to play this trick of the drag-free. So the spacecraft turn on and off its rockets to stay centered on this test mass. It does within an error, but it tries not to collide with this. Unfortunately, contrary to LISA, we cannot follow 2 test masses at once, right? In LISA, each spacecraft follows its own test mass. Here, the 2 test masses are in the same place. So we have to violate our code of conduct, and we exert a little force on one of the 2 test masses, the minimum to maintain it at approximately constant distance from the other one, and to maintain it in the satellite. We pay a price because that's very noisy. And obviously, because we are applying a force, we have to correct our acceleration measurement for this force that we have applied. But that we know because we have applied that force, and so that's easy. Okay, so that's what we flew. That's a picture of the hardware. It's a rendering, then I'll show you the real thing. The masses are 2 gold platinum test masses, very heavy, very pure, 5 centimeter of side. And the interferometer is sitting on this high stability 0-dur optical bench. You have to carry other things. For instance, you have to exert this force on the test mass. So the test mass, it's floating, but it's surrounded by electrode that we use to apply force. And by the way, we need to apply this force on LISA Pathfinder because we cannot follow 2 test masses, but we need to apply little forces and along other degrees of freedom also in LISA. So this instrument is exactly what we will fly on LISA. It's not purposely made for LISA Pathfinder. You have to play other tricks. For instance, the test mass keep charging up because of the cosmic rays, and you cannot touch them, so there is no grounding wire. So we carry ultraviolet light, so we shine light and generate photoelectrons, and the photoelectron neutralize the test mass. You have to play terrible things. For instance, you have to block the test mass during the launch of the satellite. Otherwise, by shaking would basically hold your satellite. And then you have to release the test mass once in orbit with very high precision. And so everything is a single instrument that is hosted in a spacecraft dedicated to this instrument. It goes into a central cylinder. Everything surrounds this very delicate thing. And if you want to see the real hardware, this is one of the test masses. This is now orbiting the sun somewhere in the solar system. It goes into this box here, we call the electrode housing, but it doesn't touch it. When it flies, it's 3 to 4 millimeter, depending on the side, from all surrounding. It's just floating like an astronaut in the space station, right? And everything is integrated with all this accessory that I told you. And by the way, this test mass is anyway part of an optical system, so everything must be aligned to sub-millirad accuracy and micron accuracy. The optical bench is here. This is 0-dur. This component mirrors beam splitter are attached to the bench with this technique called silica bonding. You put a little bit of sodium hydroxide between the 2 components you have to attach, and basically the glass reforms. So there is no mechanical difference between this technique and carving the thing from the bulk that you could not do. Unfortunately, the price you pay is that you get 10 minutes to do a joint, and then it stays forever. And you have to align again to sub-micron and sub-millirad and micron. And again, industry and institute made a great job in doing that. You see here the optical bench integrated with photodiode and so on. Everything is integrated in a big thing here. So believe it or not, the 2 big test masses with all accessories are linked with glass. There is no other thing that glass that connect them together. That's because of mechanical stability. You see, the apparatus is very, very complex. And I mean, before this experience, I would say, oh, this cannot work. It's too complicated. And it goes to the credit of the aerospace industry on how they could integrate such a complicated thing, and it worked like a jewel. So here you see the cylinder containing the instrument being put in the satellite. The satellite goes on its propulsion module, integrated in the fairing of a Vega rocket, which is an Arianespace rocket fabricated in Italy. And then we launched on December 15 from Kourou, the Arianespace launch pad. We navigated almost a month to reach an orbit far away from the Earth. This is the L1 point of the Lagrange 1 point of the Earth-Sun system. And that's because you want to be away from the gravitational noise and the gravitational gradient of the Earth. So we navigated for a month. We started to turn on instrument, and one key moment was when we decided to release the test mass. So to uncage from this blocking mechanism, you realize that if you fail, your mission is gone because your test mass is blocked, that cannot free fall. You heard the first traces of the test mass moving, and I don't know if you can see my project manager dancing by happiness, because this could have been the darkest day in our life with total failure of the mission. Anyway, I think I'm going late, so I will tell you what, and then I will finish what we were expected what we had to demonstrate, what we were expecting to see, and what we have seen in reality. So, as I said, this is the same plot as before. Acceleration of the test masses must be below this curve here, right? That's for LISA to work. However, ESA said, we don't want to spend a fortune on this mission, so we don't want you to push to this limit. The experience says that if you can approach, if you do a test which is within a factor 10 from what you have to reach, you learn enough that then you can extrapolate the knowledge and predict what LISA will do. So to LISA, the acceleration must be outside the gray area, below the yellow line. For LISA Pathfinder, we were only requested to be outside the blue area, which is 10 times less demanding than LISA. Even more, if you see here, we were requested to test things from a milliards on and don't care about the low frequency. Again, the reasoning was if we learn how the system works at the milliards, we should be able to extrapolate at microhertz. And what were we expecting to achieve? Well, I mean, the noise budget of LISA Pathfinder is a 280 pages book, right? If you think all possible physical effects that can disturb you. Fortunately, the leading one, the 10 item short list is this one. But to cut the story short, we were expecting to be dominated by three effects. To be at the dashed line, which is better than the LISA Pathfinder requirement, but not yet at the LISA requirement, and to be limited by three things. At the lowest frequency, to be limited by this necessity to apply a force to one of the two test masses. You apply this force with a voltage electrostatically, and you generate the voltage with a voltage generator, and voltage generator are noisy. And if you work out the electrostatics, it turns that for a given noise of your voltage generator, the larger the force you want to apply, the larger the force noise you're generating. Actually, the larger the setting of your force system, if you're prepared to counteract a Newton, you do a lot of noise. If you counteract a millinewton, you do less noise and so on. In reality, we're talking nanonewton here. The second, in this range here, we were instead expected to limit it by the intrinsic phenomenon, which is Brownian noise, the collision of the residual gas molecule with our test mass. The pressure is very low, but still it's not zero. And so this noise increases with the number of molecules, and so increases with the pressure. The lower the pressure, the less the noise. At high frequency, it's not acceleration of the test mass. At the high frequency, the problem is that you have to measure the frequency of the laser, right? You remember the interferometer noise. And despite we didn't need all this precision, we would be happy with an interferometer with a fraction of a nanometer resolution. We could develop a 10 picometer per hertz interferometer, which is the same class of interferometer LISA needs. We could demonstrate this performance, and so we were expecting at high frequency to be limited by the interferometer. We went into operation on March 1st, and at low frequency, we're bang on the prediction, right? And so better than requirement. So, I mean, the joy, I can't describe the joy when we saw this. Very close to the prediction, except at high frequency, where you see we were expecting to be limited here. That was how our interferometer performed on ground. But in space, it performed much, much better. And actually, the noise of the interferometer only sets in a much higher frequency. And it's the intrinsic noise of the interferometer, what you calculate from the textbook. And the reason is that the space environment is much quieter than the ground laboratory. So at low frequency, we got this performance here, and we were limited by the fact that we had to apply this force. But why we had to apply this force to the test masses in first place? Well, the reason is very simple. This test mass is gravitationally pulled by this big amount of matter, right? There is a big gravitational pull. Now it's so big that if you try to compensate entirely using electrostatics, no way, that's too much noise. So we made a two-step approach. We calculated the gravitational field by marking down the exact position and mass of every component on the satellite to the screw level, right? Calculated the gravitational field and fabricated a tungsten, very dense test mass that we attached here, almost 2 kilos of tungsten.
With that, you basically balance to 0, but the problem is 0 plus or minus what, right? So the name of the game here is how accurate are you in making this prediction? And you have to, to consider all the errors you can do in placing all the screws and all the pieces and so on. And our conclusion was that our error was plus or minus a fraction of a nanometer per second square gravitational pull. It's a lot of margin. You always put a lot of margin. These are million euros. But we went up and we discovered that we had done, what is this, a factor 30 better, right? We were expecting 650 in this unit, and we found 25. This is because of the margin, but also we are lucky. This is an event we calculate in hindsight has 5% probability. So we say, oh, we don't need to hold this force. Let's crank down the actuation. And as soon as we crank down the actuation, oops, we went here, right? The actuation noise, we killed the actuation noise, and the noise went down. And even here, you see the noise went down. That's not for something we did. That's because here the noise is limited by this Brownian effect, which is proportional to the pressure. And while we were playing with this, the pressure kept going down because we are venting the test masses to space. And so if you plot this level here, this is proportional to pressure. If you plot this as a function of time, this is the duration of the mission, you see the pressure going down like when you attach a pump to your vacuum apparatus on ground. And so it's not surprising that at the end of the mission, the pressure has gone so down that our measurement, that the noise level we could reach was much better than LISA, with margin all over the frequency span. And that's basically convinced LISA to go ahead with LISA. LISA, how much time I have, Maria? Another 5 minutes? Am I alone?
Yes, no, you're not alone.
It's okay?
Let's say 10 more minutes because we started a little bit late.
Okay,
yes,
10 more minutes. Oh, that's fantastic. Okay, we did a lot of experiments, right? Not just this. I give you a few examples. These are papers. There are more coming. These are papers from LISA Pathfinder. I give you an example. You see, this is a charge-induced force noise. So as I told you, these test masses keep charging up. They charge up because of cosmic ray that hit the spacecraft and generate a lot of protons. And these protons hit the test mass. We could calculate how much we expected and what the noise we were expecting using this giant 4 tools to calculate nuclear, that the high energy colleagues use. Now, why this is noisy? Because if there is any stray voltage across your test mass, and there is, because you cannot control the electrochemical potential of the surfaces too well, when in a random arrival of charges, it's converted into a random force, 1-to-1. So we were expecting that we could balance to the level that this is not a problem for LISA, but we want to demonstrate that what we had calculated was right. So we measured this charging, and this is a trace of the charging of the test mass. There is a constant slope that has been subtracted here. And so this is the noise, and the spectrum of the noise is what you expect for a Poissonian arrival of particle. Our prediction were good within a factor 2. Our giant calculation for protons were right, but we discovered that we also generate low energy electrons, and low energy electrons are not included in those simulations. Those are too complicated to simulate. But all in all, even if the rate is almost twice what we expected, the noise for LISA is within the specs. Here you see how you see the noise due to the charging, but then by applying a counter potential, you can suppress the noise until it becomes negligible relative to other sources of noise. So interesting physics also on the charging in space of this object. I had another one, but I skipped one. I'll give you another example of what we could measure. So we were hit by Micrometeroid, right? Small dust particle
Now, these are very small. I don't know how small, but very small. It's basically dust. And we measure the impact, right? Because of this drag-free system, because we measure the acceleration of the spacecraft relative to our quiet test mass, when a micrometeoroid hits the spacecraft, we see, boom, the motion, the spacecraft moving, you know, getting a big hit on a side. The drag-free system immediately sets in and restore the equilibrium position of the spacecraft, applying a counterforce. And so by subtracting these two, you can measure the impulse that each of these micrometeoroid deliver to the spacecraft. And believe it or not, it's an interesting measurement on cosmic dust, on dust in the solar system, because we had many of those hits. We searched in hindsight how many of those hits we get, and the statistics of the hit we get is the colleague found is in good agreement with what you expect from the dust released by this Jupiter family comets. Don't ask me anything because I'm totally ignorant. I'm just reading the paper. I'm a co-author of the paper, but I have to read the paper to tell you what we found. Anyway, the most important results we got is that LISA goes ahead. So even before we ended our operation, ESA decided to go ahead with LISA. So LISA is now the third large mission of the Cosmic Vision program. We are, in this moment, we are in mission in phase A. So we are completing the definition of the mission. We will have a review. We will have a review, and we are aiming to have the mission adopted in 2024, which is 4 years from now. From there on, you know, nominally speaking, the technical time to set up the mission together is of the order of 9 to 10 years. So we should be ready to launch in 33 or 34. But obviously, prediction on that long time scale, I'm too old to make those predictions. So I cover this in a great thing. For us, the main objective is to being adopted. Mission adoption is when you start cutting the metal for the flight hardware. So from there on, you're building the real thing that has to fly. Before that, you're setting up the technology and defining the mission. The phase A is basically designing the mission. I cannot show you the detail because the phase A is conducted by two competing industrial competitor, and so everything is covered by industrial secret. But I can tell you the concept of LISA has been stable for years. So here you see a rendering a few years old. You see the telescope that received the light from the distant spacecraft. The light gets distributed on the optical bench. One beam of the light goes into this box, hits the test mass, and measures the acceleration of the test mass, right? So the concept is this one is not being changed. It's only the detail that matters. There are no major technical issue. You know, this is a view graph taken from my project manager who says watch list of issues. So things that have to be, you know, kept under scrutiny. There are a few technology development that you have to do. For instance, the optical bench of LISA is much more complicated than of the optical bench of LISA Pathfinder, many components. Assembling it by hand, it's too dangerous. And so one of the investment is to have a robot able to do this very delicate bonding, this silica bonding with the proper alignment, all automatized so that you don't have human mistakes. There are detail in the interferometry. For instance, this is just one detail. You have to connect two arms, and you need another interferometer, but you cannot fly in free space. These arms move one relative to the other, so you use fiber. This is sort of cutting-edge interferometry, and so we are working to that. Somebody is working to that, but things are progressing well. The telescope, which is used to exchange light with a distant spacecraft, is not a trivial telescope because it must be stable to picometer, because if the telescope moves by picometer, you think that the distant spacecraft is moving by picometer or that there is a gravitational wave intervening between the two spacecraft. This is NASA is contributing the telescope, but the work is progressing reasonably well. I think I'll skip this. So this is too complicated. Let me say that a mission like that is a gigantic effort. It involves space agency. It's ESA, NASA, and about 10 member states of ESA. It's a big collaboration. We're talking 2 billion. But it's also supported by an army of scientists. You see, we have a LISA consortium, and this is take it as an advertisement to join the LISA consortium. And the current number of members of the LISA consortium is in excess of 1,300. So if you're interested in participating in the science of LISA or being involved, or that Greece is involved, honestly, I must confess, I don't know if we have a Greek member in the LISA consortium. Maybe yes, maybe he's even in the audience. He would forgive me. I've been out of the consortium for 3 years, chairing a committee in ESA. And so please check this website, and you will find instruction to join the consortium. And thank you very much for your attention, and also thanks to this fantastic team who made the LISA Pathfinder possible, and then LISA possible. Παρακαλώ, no, ευχαριστώ. Thank you very much for your attention.
Thank you. Thank you, Steph.
Thank you for the excellent talk. Yes.
Yes, yes, we should say ευχαριστώ. Very impressive, very impressive. I have questions.
Should I stop sharing so that we see each other's face?
It's up to you. Yes, sure. I have questions, but please go ahead. Anyone else in the audience who might want to go first? Who might have things open in their mind yet? Well, let me ask until people figure it out, because I don't see anything in the chat yet. So you said that for the sensitivity curve, the bottom of it is defined by Brownian motions. And at first, I thought that these are the Brownian motions of whatever molecules tend to be left after the launch from the Earth's atmosphere. But then you send your venting to space. So in reality, this is the ISM pressure you're talking about? So you were really limited by the ISM pressure?
No. The outer space is a pump. It's a very nice pump, but you cannot put this thing in, can you see my hands? Yes. You cannot put this thing in open space, right? It's inside the satellite. And because it's inside the satellite is miserable. Satellites are evaporating. The pressure is something like, in a satellite after a year, you're probably at 10 to the minus 4 Pascal. You are millibars, right? So the satellite is, forget. So we have everything in a vacuum enclosure. We do the vacuum on ground with a pump. We pump and pump and pump and clean it up. Then we put this thing on a shelf for a year, because that's the problem of space system or space project, that you prepare the hardware, but before the launch, right? And then we go up in space and we open the valve on a hose that goes to open space. Now, open space is a fantastic pump. No backstreaming, no oil, nothing, right? But you're limited by the conductance of the hose and the evaporation of your, and the outgassing of your box. And so that's why you see the pressure going down, right? You see the system attached to a pump, and the limiting pressure at the end of the mission was a micropascal, 10 to the minus 6 Pascal, 10 to the minus 4 bar, right? 0.1 millibar. Did I answer?
Yes, 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 of course. And anyone else? I have more, but is anyone else?
I also have a question or two, but I will ask one. So I was really impressed by the sensitivity curve that LISA Pathfinder eventually reached. You showed us what was the expectation and what you actually found. And I found it particularly interesting that it was lying below the prediction for the LISA instrument. So I was wondering, and perhaps this is a naive question,
no, it's not
will
naive.
the sensitivity curve of the LISA mission be even lower than predicted?
That's a good question. So that sensitivity curve for LISA is not the predicted, it's the required, right? Those are the requirements. right? So indeed, if we could achieve the same sensitivity, we would be better than requirement. We would be slightly better than requirement, which probably will happen. But you have to, when you design a mission, you put margins, right? That's because otherwise, you know, you don't reach your requirements. So maybe we'll do slightly better, but we cannot plan to do slightly better because we have all the margin. And honestly, despite the device there, the toy is the same that is going to fly in LISA. LISA Pathfinder is not LISA. The system is different. So there are other conditions. So I wouldn't be that optimistic that we are necessarily much better than requirement. But we might be slightly better than requirement. That's true.
Okay, thank you.
And your second question?
The second question was related, yes, think of possible questions. The other one was related to the cosmic ray flux and how this affects the test mass, which I was not aware of that, and I, again, found it particularly interesting. And I was wondering how you do the simulations. Are you taking into account models for the cosmic ray flux, and do you take the various species into account? So could you tell us something more about the cosmic ray flux?
Yeah, the simulation is simulation with the model of cosmic rays and the model of the satellite, because it's not the direct hit. It's not the direct, oops, sorry, phone call. I can't take you now. It's my wife, so maybe I should take it, but anyway. So it's not the primary, it's not the direct hit of the proton or the muons or the protons on the test mass. It's a shower generated by a muon, for instance, hitting the spacecraft, right? So you simulate this process. You need a model of the spacecraft because you have to simulate the showers, right? And then those showers charge up the test mass. Now, the transfer momentum is not a problem. The direct transfer, the fact that the charge stops in the test mass and hits the test mass, that's negligible because the test mass is 2 kilos, right? It's, the problem is that you deposit a charge that basically never discharges. If you don't do anything, the charge stays there because there is no contact, right? And so if you now have a voltage difference across the test masses, charge times voltage difference is a force, right? So your problem is no voltage difference, and it's only partly under your control because people think that metals are equipotential, but they are not because of all this charge patches effect and work function differences and so on. So you may try to balance actively, that's what we do. And then the charge that arrives doesn't generate a step of force, and so it doesn't disturb the measurement.
Okay, there is a question by Apostolos Mastiadis.
Yeah. Hello.
Yes.
Thank you very much for your. Can you listen?
Yeah.
Okay. Thank you very much for your very impressive talk. It's one of. I have one question that follows up Maria's question. That cosmic rays, except if I have misunderstood something, cosmic rays also have differences in their flux. They are variable because of the solar cycle. So do you take all this? I guess you have taken all this into account. I mean, the difference in flux that you might expect during various epochs, for example. That's one question. And then I have a more astrophysical one.
But then ask me the second question later because my short-term memory is 10 seconds.
Yes.
Okay, so yes, we have solar flares, right? This is the major variation. And actually, we have 3 papers on measurement of solar flares with LISA Pathfinder. We carried a charge detector. We carried the particle detector as a monitor, and we cross-correlated the particle detector with the charge on the test mass, so we could see the flares. Certainly, if a major solar event happens, it will spoil the data of LISA, but for a short time, right? And absolutely. If it happens, the largest one will spoil the performance for a week or a day. That depends on the intensity of the flare.
Okay.
Second question.
Thank you. The other thing is more astrophysics. In the beginning, you said something about this.
Then I'm the wrong person.
Yes, but I'm the wrong person also for the instrumental part. So I have to go to astrophysics. Today I was talking to some students about multi-messenger astronomy. In other words, gravitational waves plus some electromagnetic signals. So you said something about accretion disk flaring, and can you be a little bit more specific about? I mean,
I can be more specific in this meaning. That, for instance, maybe I should share again my screen.
Yes,
I think. Yeah. Okay.
Yeah, we see your screen now.
And let me see if I can trace the view graph back. This is fantastic. This Mac tank. So here it is. So, for instance, we expect to be able to see one of this supermassive black hole merger, both with LISA and with Athena, which is the ESA X-ray observatory, which is also under development. ESA is doing their best to have a substantial overlap of operations between LISA and Athena, that we should be able to at least detect a few of these events where we see, don't ask me too many details, but I mean, basically the idea is that the spinning of the two black holes energize the common disk around the black holes, and this causes emission of X-rays. X-rays are here, right? Causes an emission of X-rays, which has the modulation of the gravitational wave. Now, one of the reasons why for us the multi-messenger is very important, it's not astrophysical, it's cosmological. Let me see if I can show you a view graph that you know, with gravitational wave, you measure the distance to the source without the need of any candle. That's because the intensity of the wave is proportional to the energy loss, right? You lose energy through emission of waves. So the more waves you emit, the more energy you lose, and the larger is the variation of the period of revolution. So by measuring the period of revolution, you measure the intensity at the source, and by measuring the intensity here, you measure the distance. So it's a fantastic candle to measure the distance to the source, and that, some of those sources I told you are at redshift much in excess of 1. However, we don't measure the redshift. This is already a redshifted signal. And so if you can find an electromagnetic counterpart to one of these events, now you can measure both the distance and the redshift and give a big contribution to the equation of state of the universe, totally independent from other determination of the equation of motion. For the big black holes, Athena, for instance, is one of the methods. Other observatories could detect the counterpart, but there are also statistical methods to try to assess and locate the galaxy from which the signal is coming. So that's just to give you an idea. This is a bit selfish because it's cosmologists versus astrophysics. What the black holist will do with this multi-messenger information here, that I don't know. Actually, I would not take question on this because
you might be interested in gamma rays as well, because it's quite possible that these mergers give you gamma ray flashes as well.
Maybe, but that I don't know.
Thank you very much.
Sure. Oh, you had another question? Ah, no, that was the second question.
No,
see, I don't remember even how many.
Enough.
I don't see any other questions in the chat. As far as anyone else? No, my second question was about cosmography. I wanted to actually see that slide of cosmography. You said it. So unless someone has something else to say right now, I believe we're covered.
No, not yeah.
So really, thanks a lot for this great talk. We're really happy.
Sure, my pleasure.
Hopefully
and I look forward to see a few of you in LISA soon. Okay.
For the students to hear that.
Yeah, the younger generation.
Yeah, I'll be dead. When Lisa fly, I'll be dead. So Lisa, it's your toy, it's not mine.
Thanks
Ciao.
so much. Thank you.
Bye-bye.
Thank you very
Thank
much.
you.
Bye.
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 Thank you.
Thank you.